Alright friends, welcome back. In this video we're going to go ahead and cover the last section of Chapter 1 in your textbook, which is 8.1. Sorry, not 8.1, goodness, 1.8 I meant. And we're going to go ahead and take a look at other types of inequalities. So in the last video we took a look at linear inequalities, and we saw that they're basically solved the exact same way as linear equations with some extra quirks. And in this video I want to go ahead and talk about inequalities that are not linear. So we're going to start off with polynomial inequalities, and here's just a little bit of a step-by-step for how you want to go ahead and solve your polynomial inequalities. So the first two steps are steps that we have seen before in a lot of different other applications. We just want to go ahead and get 0 on one side and move everything over to the other. And then after that, once we do that, we want to go ahead and factor the polynomial that results from that. After that, the process is going to look a little bit different, and it does describe what the steps 3 to 4 are here. And I'm just going to go ahead and instead of explaining through everything, we're going to go ahead and just demonstrate by doing an example. Okay, so example 1, we have x squared minus, or sorry, not x squared minus, x squared is less than 25, and we just want to go ahead and solve this polynomial inequality. So first step of that is to not to take a square root of both sides. I want to point that out, right? So you might be very tempted to treat that inequality sign like if it was an equal, and you might be very tempted to square root both sides here, but that's not what we want to do. Instead, what we want to do is go ahead and move everything to one side of the inequality. Okay, so I'm going to do that here really quick by subtracting 25 from both sides, and that will result in 0 on the right. And we're going to go ahead and write out our polynomial here. So that's going to be x squared minus 25. Okay, so that's always the first step that we want to do is move everything to one side instead of trying to do operations on both sides of the equal sign. And now we have this polynomial x squared minus 25. It's at this point that we want to go ahead and factor this. And you may recognize this as a difference of two squares. So this would factor into x plus 5 times x minus 5. And that's less than 0. Okay? So the way that you want to continue is you want to make what's called a sign diagram. Okay, if this was just an equal sign instead of an inequality, then we could just go ahead and skip straight to zero factor property and get our two numbers and be done. But here we're not interested in where we are equal to 0. We are interested in where we are less than 0 specifically. Okay, and so what that means is we're going to have to be a little bit careful about what values we're going to be ending up with here as our final solution. Turns out we're not going to have one or two solutions here. Instead, we're going to have an entire region of the number line that represents solutions to this inequality. So I want to go ahead and talk about how we go ahead and figure out what those regions are. All right, so let's do that now. If this was zero factor property, then it would be pretty easy to figure out what your two zeros are going to be. Pretty straightforward. That would just be x is equal to negative 5 and x is equal to positive 5. Okay? So instead of just boxing those as our answer, what I want to do is I want to come off to the side here and draw a quick number line. What we're going to draw here is something that's called a sign diagram. And because these values here of negative 5 and positive 5, these are values that make the polynomial equal 0, we're going to mark those on my number line. Okay, so negative 5 and positive 5. And I'm just going to go ahead and really quickly put some zeros above that just to help myself remember that if I plug these values into my polynomial, I get a 0 out. So we call those the zeros of your polynomial. Okay? And now what I want to do is I want to go through and I want to take a look at my number line, because when you do that, what you basically do is you split up the real number line into 1, 2, 3 different regions, and I'm curious about what all of these regions are going to mean for my description over here. Okay, remember, I'm only interested in values that are less than 0. So what that's automatically going to mean, now that we have those zeros written down, is that I am going to have some open dots on these values here, and you probably can't see that blue color very well on a blue background, so let's change the green. Okay, I'm going to have some open dots on those values of negative 5 and positive 5 because I'm not less than 0 there, I'm equal to 0 there. Okay, and so what we want to do here is we just want to go ahead and pick a test value that lives in each one of these regions, and we're going to plug it into our polynomial. We're going to end up seeing if we plug in a test input, what do we get an output of? Okay, is it really going to be something that's less than 0? Well, let's find out. You could pick any candidate that lives in these regions that you want. The first one that we want to pick is just something that is to the left of negative 5 on the number line. Something easy would be to pick negative 6. If you were to go ahead and pick something in between -5 and 5, I would highly recommend that you pick 0, because when you plug 0 into polynomials, you get nice and easy results. And then on the right side of +5, you might want to pick something, I don't know, like +6. You can pick whatever you want, okay? But we're going to pick these test inputs, and then we're going to plug them into our function, okay? Or our polynomial here, I should say, right? So if we plug in -6 into our polynomial, remember that our polynomial looked like x squared minus 25. If we plug in a -6, let's see what happens. So if we plug in -6, then what's going to happen is I'm going to have -6 squared, which is 36. And then when you take away 25, that's going to give you a value of 11, positive 11, okay? And that is what we want to focus in on here, is the sign of the output, okay? So what that means is we tested -6 as just kind of like a test input, but it turns out that if you were to pick any candidate that lives in that region, you would always end up with a positive output. So what I'm going to do to kind of signify that here is just go ahead and write a plus with a circle around it to say that anything that I plug in from that region right there is going to give me a positive output. Okay? Moving on to the next one, if I were to plug in a 0, then again, the reason that you want to pick 0 is because oftentimes it's really easy to do that with some mental math. If I simply do 0 squared minus 25, the result would be a -25, and that of course is a negative result. So I'm going to go ahead and signify that any test number that I pick there is going to end up with a result that is negative, okay? And I'll just give away the punchline in that last one. It turns out that that is going to be a positive region. If you plug in +6, square that makes 36, take away 25, that's going to give you positive 11 again, okay? Now, what are we interested again? We are interested in just those regions that are strictly negative, strictly less than 0. So what that means is on my number line here, I'm only going to shade regions that happen to have a negative output. And so that is going to be this middle region right here. I'm not going to shade the other positive regions because we're not interested in being positive. We want to be less than 0 in this example. Okay, so that is going to give us that green region right there. And that's just something that we were just going to write down here as our solution set in this problem. Okay, so that would be the open interval from -5 to +5. And that represents our solution set for this example. So what the idea here is if you go back to the original example, x squared is less than 25. We're looking for all the x's that you could plug in so that if you square it, you get something that is less than 25. Apparently that will work out for you if you specifically pick a number that is in this region right here, okay? So something that is in between -5 and +5 strictly. So we're going to apply that process here yet again. For example 2, we would just want to go ahead and bring this, this 18 over to the other side. So I'll simply just add it, okay? And then that's going to result in x squared minus 7x, and then that'll actually be plus 12, and that's less than or equal to 0, okay? So that's bringing everything to one side, leaving 0 on the other, and at this point we want to factor, just kind of continuing with our steps here. So this is going to factor into x and x. We're going to have a combination of 3 and 4, I suspect, and I believe we're going to get there if we make them both negative, so that's good. So the description that we want to fit in this problem is now we want our outputs to be less than or equal to 0, okay? So contrast that with the last problem where we strictly wanted to be negative. Now we want to be either negative or 0, okay? So if you were to pick your critical numbers out of this factorization here, so treat this like an equation temporarily, this would give you x is equal to 3, that's what makes that factor 0, and x is equal to positive 4. That's what that factor would be to make that 0. So these are what we call, again, your critical numbers. And what we want to do now is skip straight to doing our sign diagram. So I'm going to draw a number line. I'm going to mark my two critical numbers, mark 3 and mark 4, and just help myself remember that these are the values that produce an output of 0 in my polynomial, so I'll mark those with a 0 there. And now I am trying to figure out which regions of the number line are going to result in some outputs that are less than 0 or equal to 0. So because in this problem I want to be equal to 0, then that means I'm going to go ahead and put some solid dots on what inputs make an output of 0. And that would be my two critical numbers at 3 and 4. We just now want to go ahead and pick a test value in each region and figure out what the sign of each region is going to be, okay? And again, you can test any values you like here. Again, probably pick 0 any region where it shows up. In between 3 and 4, if I just go ahead and do the average of 3 and 4, I get something like 3.5. And then if I were to plug in something that comes to the right of 4, I might just go ahead and pick 5, right? So again, what we're doing is we're plugging these into our polynomial here. So you could plug back into either one of these starting guys here, right? You can go ahead and go back to the trinomial, or you can plug into its factored form, whichever you prefer, whichever you think is easiest. In my opinion, I think that plugging into the factored form is easiest, because then we could just go straight over here and say x minus 3 times x minus 4. If I plug in a 0 to that, then I'm going to end up here with negative 3 times negative 4, and a negative times a negative makes a positive 12, so that tells me that this region is going to end up being a positive region, okay? If I were to do the same thing for the 3.5 and plug that in, then I'm not going to actually show those calculations here. I'm just going to go ahead and say here, when you plug that into your factored form, you're going to end up with a result that was actually negative. And then when you plug in 5 here, same thing. You're going to end up with something that is going to be positive as a result of that, okay? So just trying to save some time in the video. And again, what do we want? In this Venn diagram, we want to fit the description of being less than or equal to 0. We've already taken care of the equal to part by putting some solid dots on 3 and 4, but we want to be less than 0, so I'm going to go ahead and shade that middle region, okay, because that's where I'm negative. And then, of course, this is where we want to go ahead and write our final solution set in interval notation. So I start at 3, I end at 4, and I do want to include these values, so I am going to go ahead and include those in some square brackets, okay? And that represents my solution set for this problem. So again, the idea was we wanted to figure out what solutions or what inputs we could plug into our original polynomial so that we end up with something that is initially less than or equal to negative 18. And so what we're saying is if you pick any x value that lives in between 3 and 4, and throw 3 and 4 in there as well, if you were to plug those into the original inequality for x, you will always get something that fits this description right here that is less than or equal to negative 18. Here in the next example, same thing. We just have another polynomial here. We'll just do this one really quickly. Factor that trinomial there. So we've got x and x. Okay, so we're looking for two numbers that are going to multiply to make negative 6 and add to be negative 1. So if I were to go ahead and pick some combination of 2 and 3, probably pick a negative 3 and a positive 2, that's going to give it to us straight away. Get your critical numbers, so treat this like an equation temporarily and get your critical numbers here. X is going to be negative 2 here, and x is going to be positive 3 there. If you want to think about it this way, the critical numbers are just going to be the opposite signs of whatever you see here and here. Okay, that's a very quick way to be able to do that, all right? And then we'll go ahead and skip straight to our sign diagram. Okay, so we'll mark our critical numbers, so negative 2 and positive 3. That is where I am equal to 0, and that is part of the description that I want to fit in this problem. I want to be greater than or equal to 0. So because of the or equal to, I am going to go ahead and put some solid dots on my critical numbers there and just signify that this is where I'm equal to 0, okay? Picking some test candidates from each region. Again, picking 0 wherever that lives. That might be in the middle region. Pick whatever you want for these other two regions. Just keep it simple, right? How about negative 3 and positive 4? These are values that we're plugging back into our factored form, and we're going to see about the sign of those, okay? So if you were to go ahead and plug in negative 3 into your factored form over here, again, just kind of taking a look at how that went. If I plug in negative 3 and negative 3 into my factored form, I had my x plus 2 and then x minus 3. So plus 2 and then x minus 3. All right? So what's going to end up happening here? Well, this is going to end up being negative 1. And this is going to end up being negative 6, and that's a negative times a negative. That makes a positive. So that means that this entire region is going to be positive, and then I'll just give away the punchlines for these other ones. This one is going to be negative, and this one is going to be positive over here, okay? Now, we are interested in this example where we are greater than or equal to 0, okay? So instead of shading that middle region where we were negative, I'm instead going to go ahead and shade these outer regions here because that is where my output is going to end up being positive here. So when I go ahead and do that, I'm going to go ahead and say here that that would be the open interval from negative infinity all the way until I reach negative 2, not including negative infinity because we'll never reach it, but we will include negative 2 because that's where we are equal to 0, so square bracket on that. And we're going to unite that interval with the interval from 3 to positive infinity, including 3. okay? Because again, that is where we equal 0, and so we'll go ahead and maintain that here in our solution set, okay? So again, if you want to plug in something for x in the original inequality so that you end up with something that's greater than or equal to 0, you have to pick something that lives in one of these two green regions right here. Next example, we have yet another polynomial equation here, and so when we factor this, again, this is a binomial here. It looks like I have some common factors, so I'm going to factor out a GCF. The GCF here would simply be 4x squared, and that leaves behind x minus 2, and that's going to be greater than 0. So greater than 0, that's the description that we want to fit in this example. So we're going to go ahead and find our critical numbers really quick and easy. We do have a monomial 4x squared and then a binomial x minus 2. So remember to be setting these individually equal to 0 and solving. If you were to solve that first equation right here, then you would get x is equal to 0. If you were to solve that second equation here, you get x is equal to 2. So these are your two critical numbers here. And so when we draw our number line, we're going to mark those two. So here's 0, here's 2, and this is where we are equal to 0. Now, do we want to equal 0 here? Well, no, because we want to fit this description where we say that we are strictly positive. So not equal to 0, we want to be strictly positive. So that means I'm going to go ahead and put some open dots here where my polynomial is equal to 0. And then as always, I just want to go ahead and test each region here. So pick a candidate from each region. And here we can't pick 0 because 0 actually turned out to be one of our critical numbers. So pick something else. So maybe -1, maybe 1 there, and 3 there. Okay? So if you were to plug these in, I'll just go ahead and give away the punchlines on these pretty straight away. When you plug in -1, you're going to get a -12 as the output. So that means that this region is going to be negative. If you were to plug in +1, then that would give you a -4, actually. So that means that this is going to be a region that is also negative. And then if you were to plug in a 3, then you would get something that's positive there. So that is going to be a positive region there. So it's always important that you go through and pick a test candidate. And now again, because we want to fit the description of being strictly positive, we're only going to shade the region that ended up being positive. And of course, that's going to be this region over here off to the right. Okay? And so anything that is in green there, we're going to go ahead and include in our interval. Not that open dot on 0, though, because remember, we put that open dot there to signify that we don't want to include that. So the only values that are going to work here are just going to be the values that are included in the open interval from 2 to positive infinity, and that will be our solution set for that problem. Okay? So when you solve a polynomial inequality, you just want to go ahead and create your sign diagram, and then go ahead and shade the regions that match the description that you want to fit. Okay? Really quickly, I do want to go ahead and discuss rational inequalities in this video as well, because the process is basically the exact same. The only thing that you need to worry about is how you find your critical numbers. You're going to find those by setting the top and the bottom of your rational expression equal to 0 and solving. Okay? So contrast that with the polynomial way of doing things, which is where we just set the whole polynomial equal to 0 and solved. Okay, so here in example 5, we have this rational expression is less than or equal to 3. Remember that our first step always needs to be, we're going to go ahead and move all the terms over to one side. Okay, so when we do that, we're going to end up here with the rational expression 2x minus 7 all over x minus 5. And what I would like to do, since I am saying minus 3 here, is I'm going to go ahead and write 3 as a fraction. I'm going to go ahead and write that as 3 over 1, because what we're going to do is we're going to combine everything into a single rational expression on the left-hand side of this inequality, okay? And then I'll leave some space there, and I'll say there's my less than or equal to sign, and then on the right-hand side, I was just left with 0, okay? So how am I going to go ahead and get a common denominator? Well, typically the way we do that is we just go ahead and stick with the denominator that we get when we multiply our two existing denominators together. And so here, that's just simply going to be x minus 5, okay? That'll be our common denominator on our next line. So since the initial numerator of our first rational expression was already something that had a denominator of x minus 5, that means I'm just going to copy it down. But then the second one needs some work because the denominator doesn't yet look like x minus 5. We're going to have to introduce that to that numerator, but that denominator. But whatever we introduce to the denominator, we have to introduce to the numerator. So this is what we're going to have. And I want us to pay particularly close attention to how this works out because that was subtracting 3, remember. And so if you kind of look at this as there's my minus sign, I'm going to distribute in a negative 3. Then we can go ahead and knock that step out here as we proceed to the next line. So that's a negative 3 that I'm distributing in. So that's a negative 3 times x. That'll give us negative 3x. Negative 3 times negative 5, that'll be a positive 15. Okay? And so now I could just go ahead and clean up my numerator and combine my like terms here. So 2x minus 3x, that's going to give us negative x. And then negative 7 plus 15, that gives us positive 8. And so this is the simplified version of my rational expression there. Okay? And so now it's at this point that I want to go ahead and start to find my critical numbers. Okay? And remember that the slide before this said that the way that you do that is you set the top and the bottom individually equal to 0 and you solve. Okay? So I'll do some dedicated spaces for both here. So if I do the top is equal to 0, that's negative x plus 8 is equal to 0. We'll solve that. If I solve for the bottom here, that's x minus 5 is equal to 0, and we'll solve that. Okay? I'm not going to show the steps for solving either of these equations here. I'm just going to go ahead and share with you that x would be equal to 8 over here, and x would be equal to 5 over here. Okay? Now, if the top is equal to 0, then that means that this is a value that if you plug it in, the whole rational expression is going to turn into 0. So we call those sorts of things the zeros of the rational expression in general. However, if you set the bottom equal to 0 and you solve, these are things that make the rational expression undefined. Okay? So I'm just going to say that here, undefined. And both of these together, these represent the critical numbers that need to go into our sign diagram. And so I'm going to go ahead and do that right now. I'm going to draw a big number line here and mark my critical numbers. One of them is 5, the other is 8. So before, remember that we typically marked these by saying that 8 was a 0, so I put a 0 above. Because 5 makes the whole rational expression undefined, we would just need a symbol that would represent that. You see a lot of different things in a lot of different textbooks, but that's what I do. Okay, so now again, we just want to go ahead and pick a test value from each region, picking 0 wherever it shows up, and then picking whatever you like for the remaining regions here. And again, what do you plug back into? I would very highly recommend that you plug back into the original. That was this right up here where you had the rational expression minus 3. Again, because that was before you started simplifying, and if you made a mistake in your simplifying, then technically you would be plugging something in that is incorrect. Okay, so if we go ahead and plug into our original here, I just got my calculator that is sitting right next to me. I'm just going to go ahead and plug in some values here just for the sake of time in the video. What I'm doing, again, is I'm just taking my test values, I'm plugging them into the polynomial, and I'm seeing if the result ends up being something that is positive or negative, so I can mark those regions. So if I test 0 first, I end up getting a negative number here. So I'm going to go ahead and signify that with a negative sign. If I test 6, then I'm going to end up getting a positive number, so I'll say positive here. And then if I test 9, I end up with something that is negative, so I'll mark that as my negative region. Okay. Now, we need to go ahead and revisit our polynomial because we need to figure out what description we're trying to match. We're trying to be less than or equal to 0. So what that means for us over here on our sign diagram is if we want to be equal to 0, then I'm going to go ahead and mark my 2 zeros here. Matter of fact, that was not a 0, that was an undefined one. So I'll mark my 0 right there, not the 5. Matter of fact, I might put an open dot on 5 because I specifically do not want to include it. And then I need to mark all the regions that are, of course, less than 0. Okay, so in other words, where am I negative? So that would be in this region right here, and that would be in this region right there. Okay, so if we mark those down, those are going to be our solution sets for this problem. That would be the open interval from negative infinity all the way until we reach a value of 5. And then we will unite that with the interval going from 8 with a square bracket, because we're including it, all the way to positive infinity, and that will complete the problem. Okay, so again, the idea here is, if you go back to the very, very original inequality, and you want to plug something in so that you end up with something that truly is less than or equal to 3, then you have to pick something that lives in one of these two green regions right here and plug that in. Okay, you will always get something that is less than or equal to 3 in that case. All right, I just want to do one more example and then we'll call it a video. I know that this is going to be a long one, but hang it in there. Okay, so again, what we want to do here is instead of doing an operation to both sides, instead what we would like to do is collect everything to one side and then find a common denominator. So I'm going to go ahead and do that here. I'm going to go ahead and subtract my rational expression on the right from both sides. So we'll do that here really quick. And again, when you do that on the right-hand side, you're going to get 0. On the left-hand side, you're going to end up here with 5 over x minus 6 minus 3 over x minus 2. Or sorry, plus 2. There we go. And that is all going to be greater than 0. Okay? So now I've got my two fractions here. I now need to go through and find myself a common denominator, which I'll go ahead and write some space for here just so I have some room for that. Remember that the common denominator that we want to go with is typically going to be the one that we get by multiplying our two existing denominators together. So x minus 6 times x plus 2 will represent our common denominator. So I'll write that here on my next line, x minus 6 times x plus 2, something that is greater than 0. Okay, and then that's going to mean that my numerators are going to have to change. Well, this denominator here was missing its copy of x plus 2, so I'll introduce that to both the numerator and denominator. This denominator right here was missing its copy of x minus 6, so I'll introduce that to the numerator and denominator as well. And then we'll go ahead and do some distributive property and then talk about how this stuff is going to simplify down. Okay, and so if you go ahead and do some distributive property with that first expression there, distribute in a 5 into both terms, that's going to give you 5x plus 10. And then don't forget on this next one, since we did subtract the 3, we have to look at this as saying that we are distributing in a value of negative 3 to both terms. Okay, and so negative 3 times x is negative 3x, negative 3 times negative 6 is positive 18. And then just continue to simplify this and condense it into one rational expression. So combine some like terms, I'm going to end up here with 2x plus 28. All over, and I'm just going to encourage you to leave this factored instead of having to expand this all out. And that is going to be greater than 0. Okay, so we've taken what we originally had. We took the entire left-hand side, subtracted off the right-hand side. We found a common denominator, and we condensed it all into one single rational expression here. It's now time to find those critical numbers. Okay, so we're going to set the top equal to 0 and solve, and we're going to set the bottom equal to 0 and solve. Okay? So in the top, I've got 2x plus 28. I'm going to set that equal to 0 and solve. And if you do the work on that, you will find that x is going to be equal to negative 14. Okay? Over here on the bottom, if I were to go ahead and set this equal to 0 and solve, this would be something that we can apply the zero product property to solve here. That's just simply going to give us results of positive 6 and negative 2. Okay, so these are all going to be critical numbers. Remember that this one over here, this is what we call the 0 of the rational expression. That's the input that makes the output 0. And over here, these are the inputs that make our rational expression output something that is undefined. Okay, and so we're going to need to mark all of these values on our sign diagram, which we'll go ahead and get to drawing right now. Okay, so in order, please, right? So we have negative 14 all the way out back here, and then we've got negative 2 to follow up, and then finally positive 6. All right, I'm going to mark my 0 value here, and then these are my two values that make my rational expression undefined, so put some unhappy faces there. Perfect. And now we just need to pick test candidates, okay? And so we do need to pick candidates that live in all of the regions that we've separated the real number line into, picking 0 wherever it shows up. It's going to show up right there. And then just picking something simple and straightforward to do these other regions here. Doesn't need to take all the time in the world, okay? And again, I'm just going to go ahead and use the calculator here to figure out what my output signs are going to be. This is not something I'm going to actually demonstrate in the video because we've talked a lot about how to evaluate in the calculator. So if I were to go ahead and plug in a negative 15, and keep in mind, I'm going to go ahead and plug that into my original problem here. This is before I tried to find a common denominator. This is before I tried to simplify it down. Because again, if I made any mistakes in that work, then I would be plugging into something that is incorrect from the start. So I'm just going to go ahead and plug into this expression, the 5 over x minus 6 minus 3 over x plus 2. Okay, if I plug in negative 15 into that, I get something that is going to be negative, and I'm just going to continue to plug through. If I plug in negative 3, I get something that is positive. If I plug in 0, I get something that is negative. And if I plug in 7, I get something that is positive. Okay, so what region were we specifically interested in? We are interested in the regions that turn out to be strictly positive. Okay, so not greater than or equal to 0. We want to be strictly positive as our description that we want to fit here because it says greater than. Okay, so what that's going to mean is that every single one of these critical numbers is going to have an open dot because it would be at these values that my rational expression turns out to be either 0 or undefined. So I don't want to include any of those, but I do want to include the regions that I am positive. So that is going to be this region right here between negative 14 and negative 2, and then this region starting at 6, not including 6, and then going off to positive infinity. So let's go ahead and write that down. That's going to be the open interval from negative 14 to negative 2. We're going to unite that with the open interval from 6 to positive infinity, and that will complete the problem. Okay, so this is going to be our solution set for this rational inequality. Okay, so again, following the steps, That's all I have for this video, but you just want to follow the steps here. Instead of doing operations to both sides of your inequality, you do want to do that first step. Make the right side equal to 0, or combine everything to one side and leaving 0 on the other. You're going to combine and simplify your fractions here if you have a rational inequality. You're going to factor the polynomial if you have a polynomial inequality. And then just continue to find your critical numbers, make your sign diagram, and get your solution set that way. So I hope that this video has been of some help to you. Sorry it was a little bit long, but remember, you can always fast forward through your videos and whatnot. So let me know if you have any questions. Thank you very much for your attention, and I will speak to you in the next one.